He's the professor in the Department of Quantum Computing at the Technical University of Munich. His research, where his research interests lie in computational physics, statistical and non-equilibrium quantum computing, condensed matter physics, as well as quantum Monte Carlo. And he's going to talk today about quantum computing applications. Thank you very much for being here today.
Yeah, thanks for the nice invitation to this nice conference. So let me try to share the screen here. Okay, does this work? Do you see that?
Yeah, works.
Okay, perfect. Okay, yeah, and yeah, thanks to all the participants for staying so late into the evening of the conference. And yeah, as the title says, I'm talking about quantum computing applications. So what people think or imagine how one could use current or future quantum computers for practical purposes. And I mean, so you can structure my talk as a journey from ideal quantum algorithms, so which are supposed to run on idealized quantum hardware, to more like NISQ-oriented versions, which would be compatible with or can deal with limitations of the NISQ-era, right? So let's start with the more ideal ones. And yeah, I mean, I guess one of the most arguably famous algorithms in this respect is Shor's algorithm for integer factorization. So, I mean, what we're talking about is like factoring, for example, 15. I mean, this is of course simple and not challenging, but if I give you a slightly larger number, it will be really tricky to do this in your head, right? And yeah, Shor devised a quantum algorithm which would solve this runtime polynomial with respect to the number of bits to represent such a number. And what is always mentioned in this context is if this is a threat to the RSA crypto system. And yeah, I mean, with current quantum hardware, this is not really feasible to, I mean, yeah, to pose a threat yet. But of course, it's also interesting in its own right, this algorithm. And I mean, in the context of this talk, I mean, I'm of course not going through all the details. I just want to sketch the basic idea. So the main thing here is to reduce factoring to order finding. So in the end, we will have an algorithm which consists like basically all classical parts of which can be run efficiently on a classical computer. But then there's one subroutine, so to say, and this order finding, which would then run on a quantum computer. And what this means is order finding is the following. So when you have given two integers x and n, then we look for the largest positive integer r, such that x to the power of r equals 1 modulo n. Okay, and then in case r is even, we can apply this binomial formula to factorize x to the power of r minus 1 into these two factors. And then, I mean, under some probability assumptions, at least one of these will have a common non-trivial factor with this capital N. So the capital N is the one which we try to factorize. And the main ingredient to solve this order finding problem is by quantum phase estimation. So this is a nice example which highlights also the superposition principle, for example, of quantum mechanics. But yeah, as I said, it's actually not, I mean, running this algorithm for really, posing a threat to RSA is not really possible with the current hardware. And in this context, by the way, I also want to point out this paper here. So, I mean, this works with noisy qubits, but you need a lot of them, right? So, you're still not there yet. Okay, let's, I mean, briefly just explain this or highlight this phase estimation algorithm. And I mean, I'm just trying to motivate or why this intuitively works. And the idea is that we realize that this order finding problem is kind of equivalent to saying that this function f of a defined to the x to the power of a has period r. So f A plus R equals FA. And now you see that we look at something which is periodic, and I mean, it makes sense to understand or investigate this Fourier transformations, right? Because a Fourier transform can somehow find this periodic pattern, and that's why in this quantum circuits there's a Fourier transform or inverse Fourier transform actually appearing here. And this phase estimation algorithm also makes use of the superposition principle. So by applying this tensor product of Hadamard gates, we put this input state into a superposition. And the trick is then to use a controlled U gate, where this U here is multiplying its input in binary representation by some number x. So we get, so to say, due to this unitary gate, a superposition of x to the power of j modulo n. Okay, and right, in the interest of time, won't go into details, but in the end, what this algorithm yields is a fraction, where the denominator in this fraction, so this order here, is our thought order. And in the next step, I will, also mention a very famous and important algorithm, this HHL algorithm for linear systems, and also counts this more into this ideal algorithm, so in the sense of running on idealized quantum hardware. And first of all, this HHL is named after the authors of a paper from 2009. And I just want to mention here that this uses in some implicitly also quantum phase estimation. And it has a runtime, which, and the critical part is that this scales logarithmically in the dimension, right? So the n here would be the dimension of the matrix A here. And it also depends on the condition number of A. This is a kappa here, on the sparsity pattern. So it is required that this A is sparse, and on the desired accuracy. And of course, naturally, because linear systems are kind of ubiquitous, right? You would think this has a wide range of applications, and I'm just listing two thoughts or ideas for using this algorithm. But in general, of course, linear systems are really appear everywhere. But it turns out it's actually a little bit more complicated. And this was pointed out, for example, by Scott Aronson in this paper here. And so there's basically a requirement checklist which you have to fulfill to really use this algorithm without losing this exponential speed up advantage compared to a classical algorithm. So, for example, we need to be able to prepare this right-hand side, so this B here, as a quantum superposition. So in some sense we need quantum RAM. And here you already see, like, even if you just want to individually, so to say, specify each entry, we already lose the quantum advantage, because this would already have runtime order n, right? And what the algorithm also assumes, and of course this is all discussed in the paper, this original paper up here, that you have to be able to apply this matrix exponential, so basically it's a unitary time evolution, and you really need the sparsity of this matrix. Then it's also required that this condition number is well behaved, so this kappa cannot grow with the dimension, and then the output state x is also likewise returned in a quantum superposition, right? So you cannot just if you need this thing as a long list, you again lose the quantum advantage, right? So you need to have an application where you can, so to say, extract the relevant information from this superposition. So in summary, I just want to say that there are several caveats, so to say, associated with these more idealized quantum algorithms. And but on the other hand, this research direction also led to quantum-inspired algorithms. So the idea would basically that now you could also try to simulate as a quantum part of such an algorithm on a classical computer and get a new viewpoint, so to say, on existing algorithms. This is just a very interesting viewpoint here. Okay, and now let's dive, so to say, more into the more NISQ-era applications. And the so-called, first of all, so-called hybrid classical quantum computing. And so the idea, so to say, here is to somehow split the work between a classical and a quantum computer. So, in particular, in this quantum variational eigensolver, which I will discuss in the following, we want to find or approximate the ground state of a quantum Hamiltonian. And the main idea here is that we use some trial wave functions, this psi theta here with some parameter theta, and the theta could be, for example, the rotation angles in a quantum circuit, but the theta are typically classical numbers. And now the quantum circuit or quantum computer would compute these expectation values of tensor products of Pauli matrices, and these Pauli matrices precisely form this quantum Hamiltonian, which we try to simulate. And now what the classical computer does, it sums up all these terms in the Hamiltonian. So this this H alpha here, these prefactors appearing up here, and the classical part also optimizes this variational parameter theta. Okay, so this is done by classical optimization, and then you obtain ideally a good approximation to the ground state wave function of the Hamiltonian. And I mean, specifically, I just want to point out, I guess, the first paper or kind of inventing this principle. And of course, this was, I mean, still more like a toy model application. So they constructed a minimal model Hamiltonian and used it to get this bond dissociation curve of helium hydrogen, so this curve here. And actually, in this studies, I used a photonic quantum computer, so they work with photons here. But I mean, it's demonstrating that this general principle works for so to say real-world applications. And here's a related study by the IBM collaboration. So this was from 2017, but in the same spirit, right? You have this kind of a quantum circuit where you have some variational parameters in it, and then you optimize these by a classical algorithm. So here's this aspect in more detail. So for example, typically you have single unitary gates. These are these purple boxes here with these parameters, and then there's one entangling unitary, which kind of, I mean, in this case consists of C0 gates, which would, I mean, as the name says, like entangle these qubits, and then you put this into sequence, and this is in the end your ansatz for this variational wave function here. So in the same spirit, and this is now kind of leaving a little bit the application to quantum chemistry or quantum ground states, but one can use or exploit the same principle for quantum optimization, and this is this QAOA algorithm, which you might have heard about. So in some sense, you could regard this cost function here as a Hamiltonian, but here's the idea that you use this for a general optimization problem. And now the principle is the same. So we also have some trial wave function, but in the end we imagine that this is in some sense a classical cost function. So we don't want to solve a quantum problem, but a classical problem, but we use a quantum superposition principle to achieve that. And one often cited application would be, for example, this Max-Cut graph problem, where this algorithm where you can actually encode the cost, so to say, in such a actually spin form. Okay, so this concludes this first, or this part of the talk, and the next one is a little bit in some sense has some overlap with that. So we already talked about simulating like quantum chemistry applications, and I just want to highlight this again. So I mean, the idea in some sense was famously proposed by Richard Feynman use a quantum system to simulate another quantum system. And yeah, right, as I just mentioned, these topics are interleaving, so I'm showing this one of the same plots again for this quantum chemistry application. And in this context, I also want to highlight or point to a recent preprint by the Google Martinis group, where they used, I think, strings of hydrogen atoms, just again to demonstrate that a digital quantum computer can be used for quantum chemistry applications. Okay, but there's not, besides quantum chemistry, so to say, there's another canonical quantum systems or quantum systems which would be amendable for digital quantum computers, and these are strongly correlated quantum many-body systems, right? And of course, the idea that because the inherent quantum language is again the same, it makes sense to simulate this on a digital quantum computer. And these graphs which I show are actually from people from Munich here. This work, and specifically what the A panel shows is a trotterization of the unitary time evolution operator. So this is of course well known that you can kind of trotterize the time steps in the of the Hamiltonian, because you have typically nearest neighbor terms in the Hamiltonian, and this maps then directly to such a quantum circuit diagram. So by the way, this is also how you would typically simulate or try to simulate such a quantum time evolution on a classical computer, but of course it fits directly to a quantum circuit. And yeah, here are some results. So the panel E here would be the exact time dynamics, or numerically exact time dynamics. Then this is the error which you incur due to the trotterization, and this is the result when you use the actual quantum computer. So in this case, IBM, one of the IBM quantum computers. All right, and now the last main section of the presentation is on quantum machine learning. And this is, I would say that this topic is already so large that you could, so to say, for each of these sub panels, you could start a separate conference. So first of all, let me explain that. So this goes back to Maria Schuld, I think, where there's just a categorization of quantum machine learning in the sense of, do you mean classical data or quantum data, or do you mean a classical algorithm or a quantum algorithm, right? So there's just this categorization. And of course, this upper left one would not be actually called quantum machine learning because everything is classical. And what I will focus on here will be more the right side of this panel. So using a quantum algorithm, and it's just, and of course, as I said, like, this is so large that I can only highlight some aspects of it without the exclusive extensive or encompassing enumeration of all aspects of that. So one study I want to point out here is an interesting idea of using a quantum Hilbert space, so to say, as nonlinear feature map. And the concept of a feature space is illustrated here. So you have in this, in this schematic 2D plot, you have red and blue dots which you want to separate, but you cannot, put a line through this plane which would separate them, right? But on the other hand, if you find a mapping which projects this into some higher dimensional feature space, then it might be possible to separate the data points. And this is, of course, well known in classical machine learning as, in the context of support vector machines or kernel methods. And our idea here is to actually make the quantum Hilbert space this feature space. And it's a concept here. And for details, please consult this paper here. And I used, I think, in this case, a photonic system or quantum computer. So this is people from Xanadu actually, and and just as a proof of principle, say applies this to some toy model data set. So So you see that this separation in some sense of the blue and red dots works reasonably well. And another, large field, which I can only more mention or here, is quantum sampling. And the main idea is basically to use the squared wave function as or interpret this as a probability distribution, and then as a classical probability distribution. So the interesting aspects come from all these complexity classes. So one can basically first of all define and then also characterize different complexity classes, and in some cases even like show really or prove that a quantum circuit or quantum computer has an advantage compared to a classical computer. So in some sense it can represent certain probability distributions which you could not effectively represent on a classical computer. So another interesting aspect I want to highlight in this context is regarding analytic gradients, which you can compute with like quantum hardware, so to say. And of course, when you want to optimize some parameters in a quantum circuit, you ideally want to find a gradient of your cost function with respect to these parameters. And here this parameter would be the mu here. So imagine that this u is encoding a quantum circuit, so it's a unitary time evolution of a quantum circuit. And then it turns out you can actually write this derivative of this cost function with respect to this mu as by this parameter shift rule. Okay, so the details are in this paper here, or also in other papers. But first of all, this looks like a finite difference approximation, but it's actually analytically exact. That's the main or interesting point here. And it also works for certain gates, but this is really an analytically exact relation. And in practice, this would mean that you run your quantum circuit or evaluate your quantum circuit twice with these shifted parameters, and then you obtain the gradient. That's a nice aspect here. And I also want to point out something which is a little bit of a caveat in training such quantum circuits. And there was a study which highlighted that at least for higher dimensional quantum circuits, you could run into the problem that gradients are almost zero or vanishing. And basically this is due to the concentration of measure in this, in this case, equatorial region. But now we have to imagine this is a high dimensional sphere. But just some heads up, so to say. So in the future, we might run into issues when actually computing gradients of larger quantum circuits. Right, and the final slide on quantum machine learning is about quantum Hamiltonian-based models. And this is also a relatively recent preprint here, where the main idea is that so the goal is that you want to construct an ansatz for a variational density matrix. And the main aspect here is to split it into in some sense, classical part. So this p theta of x would be a classical probability distribution. So here it appears again in this panel. This rho theta here is a diagonal matrix, but then you conjugate that with a unitary matrix, this U, so from the left and right, and this forms your ansatz density matrix, so to say. And schematically, this is affected by this quantum circuit here. And then you can use it, for example, to approximate a thermal state of this form. So the idea is we want to find variational parameter theta and phi such that our rho is close to this sigma beta here. And to do that, we can use a relative entropy as distance measure. So now this is directly, suggests itself to use this as a cost function. And for example, in this plot, they show the results of this endeavor. So just a, so to say, a reconstruction for the density matrix of a, I think, of a Ising type Hamiltonian in this case. All right, this brings me to the conclusions. So I would say some main message of the hybrid quantum classical algorithms would be that these are in some sense able to tackle or deal with NISQ limitations, because if we have a variational principle, I mean, every good ansatz is in some sense usable, and this also works even if if there's a noise or noise associated with a quantum computer. And yeah, several works are actually now demonstrating at least proof of principle applications of using a quantum computer for simulating physical systems. And I mean, in concerning this quantum machine learning, I mean, I've only scratched, so to say, the tip of the iceberg. So there are many other related works, for example, on quantum generative adversarial networks, on quantum convolutional networks. So I cannot go into all of these details, but this is highly interesting. But on the other hand, I guess there are also many open issues. So for example, how would you even transfer large amounts of data into or out of a potential quantum computer, right? Okay, yeah, so that's it. So thanks for your attention, and then I'm happy to take questions.
Thank you, Professor Mendl, for this very interesting and illuminating talk on quantum computing. I will now turn over the moderation to Professor Emanuel Bloch for the questions.
Okay, thanks, Nina. So there's been one question saying that in the plots of the molecular potentials calculated by a variational eigensolver, there seems to be a systematic deviation from the theory curve. Is this a fundamental limitation of the method?
Yeah, I'm not exactly sure which plots this refers to here, but I mean, okay, so first of all, it is one has to take into account that these are really still in some sense toy model systems, right? So the use the largest one I've seen then was in the order of 12 qubits, and I mean, of course, you could still simulate this on a classical computer, but of course, the idea is that as you increase the qubit numbers, this becomes like in the end only feasible on a quantum computer. And I would say, I mean, on top of my head, that a lot of approximations also go into your model Hamiltonian, right? Because this, for example, this chemical overlap integrals, these are computed beforehand on a classical computer, and what the quantum computer then actually solves is like a highly reduced model using written in terms of these Pauli sigma matrices. So of course there are a lot of approximations going into that until even the quantum computer can start its work.
Okay, I don't see any further questions from the audience, so maybe I can briefly ask one final question. So in these variational eigensolvers, of course, scaling is always the question, right? So the number of measurements you have to do with the size of the problem. Can you say something about the scaling properties of these problems?
Yeah, let me just for a second go back to that. Yeah, that's, I mean, right, there's a sampling issue, so to say. Okay, I mean, as far as I'm aware of, there are also works which try to, again, tackle this with machine learning, but then somehow classical machine learning in the sense of to reduce the number of measurements you would require, right? But I mean, I would have to look this up in detail. But right. Certainly that's a good question. Yeah. So if you so to say need to sample or measure forever, then it's also going to be problematic in the end.
Yes, I think that's a crucial question. Okay, thanks a lot, Christian, for the nice talk. I pass over to Nina again. I think we're out of time. Moving right into the next talk already.